Our next example says write the given sum in sigma notation. Try to come up with 3 different ways. So we have 3 squared plus 4 squared plus 5 squared plus ... plus n squared. So what does it mean by 3 different ways? Well, let's start off with one way. Our index can start off with 3, and it would end at n, and then each term that we're adding is in the form I squared. So this is one possible answer to write that summation into sigma notation. So let's see if we can come up with another way. What if I had my sigma and I wanted to start off at a lower index of something other than 3? What if I wanted to start at I equals 1? Well, in order to get my first term, then if I started at 1, in order to get to a base of 3, I'd have to add 2 to that. So I'd have I plus 2, and I would need to square that. And so if I plugged in I equals 1, then I'd have 3 squared. If I plugged in I equals 2, then I would have 4 squared. So that seems okay. But something to note is that we would need to stop earlier. Instead of at n, we would need to stop at n minus 2, because my last term, I would have 1 plus 2 squared plus 2 plus 2 squared plus ... And then my last term would be n minus 2 plus 2 quantity squared. This is equal to 3 squared. 2 plus 2 is 4, so that would be 4 squared. And then what happens is negative 2 and positive 2 give us 0, so our last term would be n squared, and that's what we wanted, so this is a sufficient summation. Let's go ahead and come up with one more way to write this. So let's say I wanted to start at I equals 0. So then I would need I plus 3 squared, and my upper index would need to end at n minus 3. So here are 3 different ways to write this sum. Here's a theorem. It says if c is any constant, that is, it does not depend on the index I, then part 1 of the theorem says that if you have a summation of some constant times something that's affected by the variable, you can actually pull out the constant outside of the summation, and those will still be equal. Part 2 of the theorem says that if you are summing a sum, you can break those into 2 separate summations. And part 3 of our theorem says if you are summing a difference, you can split that up into 2 different summations and then subtract them. So you can find the proofs of these in the textbook, but let's do the last one here. So I have my sum. It's starting at I equals m, and then my upper index is n of a sub I minus b sub I. So if I plug in my lower index, then I'm going to have a sub n minus b sub m, and then I'm going to increase the index by 1, so now I'm going to have a sub m plus 1 minus b sub m plus 1. And let's do one more for this. So I have a sub m plus 2 minus b sub m plus 2. And then this is going to keep going until I add my last term, which our upper index is n. So I have a sub n minus b sub n. And that's going to be the last term there. So what I can do now is I can just drop the parentheses and I can group all of the a terms together. So I have a sub m So those are all of my A terms. And then notice all of the B terms are being subtracted. So if I were to group all of those together, I would have plus, and then negative b sub m minus b sub m plus 1 minus b sub m plus 2. And then my last term would be b sub n. So we have that now. And in my second grouping of parentheses, essentially for all of the b values, each one of those is being subtracted. And so that means that we can factor out a negative 1. And if I factored out a negative 1, then all of these would be added now. But each of these groupings is just by definition the summation from I equals m to n of a sub I minus the summation from I equals m to n of b sub I, which is what we were trying to prove. Item 3 here. So this fancy little symbol just indicates that we have concluded with our proof. Let's just take a quick moment to prove the first part of this theorem. I know it says we're going to prove the last one, which we just did, but why don't we spend some time proving the first part of the theorem as well? So I have the summation from I equals m to n of c times a sub I. So if we were to expand that out, my first term would be c times a sub m plus c times a sub m plus 1 plus c times a sub m plus 2 plus, and this would keep going up until our last term, which is c times a sub n. Now notice that all of these terms have a constant in common, which means that we can factor that constant c out, and that would leave us with a sub m plus a sub m plus 1 all the way up until a sub n. And by definition, this is the same thing as c times. I can condense all of those terms inside the parentheses to I equals m, and our upper index is n, of a sub I, which is what we were trying to get to here. So once again, we have proven this part of the theorem. Here's another theorem. If n is a positive integer, then the following three summations have these identities. And these are important, so please make sure that you memorize them. You can see the proofs of these in the textbook, but let's do the first one, which is short and really interesting. So I have my summation from I equals 1 to n, and if I were to expand this, my first term would be 1, my next term would be 2, and then 3, and then my second to last term would be n minus 1, and then my last term would be n. So what I want to do here is I want to rewrite this summation I forgot the I here, so I. So I'm going to go ahead and rewrite this summation, but I'm going to do it in descending order. So I'm going to reverse the order. So my first term is n. My next term is n minus 1. My next term is n minus 2. And my second to last term is 2. And then my last term is 1. So why did I do that? Well, what would happen if I added these two things together? So 1 plus n is the same thing as n plus 1. And then if I added n minus 1 plus 2, that would be the same thing as n plus 1. Do you see a pattern? So n minus 2 plus 3 would also give us n plus 1. And this is going to continue on. So n minus 1 plus 2, that's going to simplify to n plus 1. And then lastly, if I add n and 1, that is also n plus 1. So that's what it looks like on the right-hand side of our equal sign. If I were to add these two things together, notice that they are the same thing. And so that would just give me 2 times this summation. And on the right-hand side, I'm adding together n plus 1 to itself n times. And so that is the same thing as n times n plus 1. And if I wanted to solve for just the summation, what I could do is I could take this and divide it by 2, and then take this side and also divide that by 2. So those are going to divide out. And I'm running out of space, so I'm going to come off to the side here. So if we divide both sides by 2, we get the summation from I equals 1 to n of I is equal to, the right-hand side of our equation we see is n times n plus 1 over 2. And that is what we wanted to show right here. So that concludes the proof of the first part of our theorem. And again, make sure that you have all 3 of these formulas memorized. They're going to become quite important later on. So make sure you have these memorized. And if you're curious, there are resources where you can see the proofs of the remaining 2 parts of this theorem. So Carl Friedrich Gauss is the famous mathematician behind the sum of n consecutive positive integers proof. The legend goes that Gauss was only in elementary school when a teacher asked him to sum all of the integers from 1 to 100. He quickly answered with 5,050. Some accounts say he was punished for his answer, while others say his teacher was amazed. This was nearly 300 years ago. So essentially, the story goes that to keep his class busy, this elementary school teacher asked his 3rd graders to sum the first 100 positive numbers. So 1 plus 2 plus 3 plus 4 plus ... all the way to 100. And Gauss, being the brilliant mathematician that he is, was like, well, what if I reverse it? And he noticed that all of those vertically add up to 101. So we could do 100 times 101 and divide that by 2. 100 divided by 2 is 50, so 50 times 101, if you multiply those together, gives you 5,050. So that is the story behind the proof of this theorem.